Hi, I am Angela Mark Piwalag, and I'm honored to present our paper entitled ChemBond, an educational mobile application for the mastery of binary ionic bonding topic in chemistry, on behalf of my co-authors. The presentation would follow this sequence. I'd like to begin with the research background, methods, salient findings, conclusions, and of course the references and some acknowledgement. The principal goal of science education is to produce a scientifically literate community. This can be achieved during this era by integrating different information and communication tools available to make teaching and learning of science more interesting, versatile, and goal-oriented. This rapid development paved the way for increased student engagement, motivation, and learning. Despite the advances in ICT development and the great level of improvement in science and technology, science teachers still report that they are facing many challenges and also opportunities with regards to science education. One of the problems found in the literature is that most countries integrate ICT only through routine type of task like sporadic and mechanical retrieval of information from the internet. This highlights the fact that the use of ICT in education do not necessarily transform science education for the better. More so, there is a huge responsibility put onto teachers in how they select and evaluate appropriate ICT tools to integrate in the science teaching and learning process. One of the ICT tools used widely in education are mobile applications. Mobile technologies for learning are handheld devices that support individual and collaborative learning. The use of mobile technologies is currently revolutionizing and transforming traditional and conventional classrooms into a more interactive one through applications that enhances students' learning. In addition, mobile learning provide opportunities for students to engage in problem-solving based learning activities. The features of mobile applications include time and place flexibility, ubiquity, and easy accessibility, which make it valuable in science education. Moreover, mobile applications can be effectively used in the classroom when they are used as part of blended instruction. Students often find chemistry to be very challenging rite of passage on their way towards achieving various science, technology, and mathematics fields. The same authors also posited that students experience difficulty since they simply memorize facts and formulas instead of understanding the concepts and developing fundamental problem-solving skills. More so, students also find chemistry difficult due to its abstract nature. In addition, chemistry deals with a number of abstract concepts which are necessary to explain the physical world. In response to this, many chemical educators have already utilized mobile phones for education purposes. There are currently a good number of chemistry mobile applications that can be used in educational setting or even by chemistry professionals. A review by Libman and Huang summarizes the different mobile applications for chemistry as reference or study guide, molecular viewer, for research, utilities, and as periodic table. Currently, there is no mobile application yet available on binary ionic bonding, thus this study aimed to design, develop, and evaluate an offline mobile application called ChemBond. The study employed a design and development research design and a quantitative descriptive research design. The research process is summarized in Figure 1. A mobile application that can be used as instructional material in teaching binary ionic bonding was designed based from the different recommendations found in the literature. Based from the interface and features of the app design, the application was developed by software developers from the university. It was then alpha and beta tested by experts in IT, chemistry, and chemistry education to determine glitches and inaccurate concepts found in the application. After validating the app, one class of students in a nearby high school was asked to evaluate the application. The interface design of the application is shown in Figure 2. Once students open the application, they will be welcomed by a message as shown in Figure 2A. Once the app has completely loaded, the students will be directed to the page shown in Figure 2B. While Figure 2C shows the contents found in the application when students choose the practice mode. They will be provided with the concepts, examples, and practice exercises. The application mechanics is summarized in the following steps. The student is prompted to choose whenever they will do practice or assessment as shown in figure 2b. Once students choose practice, important concepts and rules in ionic bonding are shown for students to learn as shown in figure 2c. After learning these concepts and rules, the students will be directed to a page where they can manipulate the application by choosing which element to pair with and determine correctly the subscripts. After doing some trial and error based from the element's charges, the student will submit their answers or attempts by clicking the icon combine as shown in figure 3a. If the incorrect details are inputted in the application, the app will show a prompt, try another compound, in the screen. Once the user correctly determines the correct compound, he can proceed to the next stage. The next activity will require the students to choose whether he or she will give the compound name, molar mass, and the uses of the compound. If the user chooses the naming icon as well as the molar mass icon, he or she will have to answer what is the name of and the molar mass of the compound from the three choices provided. If the user is not sure how to name the compound and calculate the molar mass, the student can directly click the question mark icon located on the left side of the screen to be provided with the rules in naming ionic compounds and the steps in calculating the molar mass. The user can also click the application icon to know what is the function and the uses of a certain compound. After practicing, the user can proceed to assessment part wherein they can input their name and class code to register as shown in figure 3b. The scores will be then directly connected to a website wherein the teacher can have access to the students' scores. After answering the 15-question assessment, students can get their scores. The ChemBond app was evaluated using the researcher-made evaluation rubric and the intrinsic motivation inventory. The researcher-made application evaluation rubric was utilized by 5 chemistry teachers to evaluate the ChemBond, while students answered the revised IMI in terms of activity perception. The researcher-made application evaluation rubric is composed of the accuracy of concept, attractiveness, function, accessibility, and interactivity, and is shown in Table 1. It was subjected to a thorough content and phase validation by chemistry and science teachers, and the instrument was then pilot tested for reliability and validity. The Krippendorf's alpha was utilized as the inter-rater reliability measure. The instrument was found to be at alpha 0.82, which is considerably reliable. Here are the salient findings. The app was evaluated in terms of 5 criteria set based from the literature review. The results are summarized in Table 2. As shown, the app has been rated to be very good in all criteria, and it is noteworthy to mention that interactivity has been recorded the highest. This is important since effective integration of technology in the instruction is not limited only in giving instructions and information, but also when students are encouraged to engage in the learning process through interactive features. The evaluators scored the app least compared to other criteria, although it is still considered to be very good. The least score given could be due to the fact that the application may vary its function based on the mobile phone used. To test for the functionality, the evaluation was not made using a mobile phone with pre-installed app, but instead the evaluators were asked to download it by themselves and install it. This would allow a more authentic scoring of the application. And with this, it was found that the application really vary its functionality based on the model and brand of phone used. Several verbatim comments and suggestions are shown in figure 4. This is from students who use the app, which supports the evaluation of teachers as shown in Table 2. As shown in figure C, I like the apps. It can help me to more understand the topic about chemistry. Keep up the good work. This highlights the quality of the application being interactive and at the same time attractive. Figure 4b, it is good. I can easily share it to my classmate using Bluetooth or share it, which notes the accessibility characteristic of the application, while figure 4c, The app is not logged and easy to manipulate, which supports the functionality of the application. As shown in Table 3, our respondents reported to agree most that the mobile application has a value in it and they will use it again, as shown in statement number 25. This could imply that the students find the application to be useful in their mastery of the topic. This is also consistent with the findings that the application allows user to effectively interact with the different features, contents, and functions. Students also find the application to be useful in improving their concentration, as shown in statement number 4. While concentration is significantly related to the learning process and is considered to be the fuel of mental operations involved in the acquisition of knowledge. Students also did not agree that they were forced to do the activity, as shown in statement number 14, and that the use of mobile application was boring, as shown in statement number 12. As a conclusion, this study aimed to design, develop, and evaluate a mobile application that can be used to develop mastery in binary ionic bonding concepts. A mobile application called ChemBond was designed based from the recommendations taken from the literature. It was then developed, validated, alpha and beta tested by both IT experts and chemistry educators. Necessary improvements were then taken into consideration after the validation. The final application was then validated. It was then floated and validated to high school students in a nearby high school. It was found that the mobile application is interactive and attractive as rated by students. This interactivity and attractiveness could be due to the unique features and functions of the applications where students can explore and do trial and error. There are assessment tasks which allows respondents to interact and learn from their mistakes. More so, the use of mobile application also developed the intrinsic motivation of the respondents, particularly in terms of their concentration and their willingness to use it again. This suggests that the mobile application can be used to teach and master binary ionic bonding topic in chemistry. This work was supported by the University of Science and Technology of Southern Philippines under an institutional research grant. Here are the references. Thank you very much, and I am now ready for your questions.